All right, so in this video, I want to kind of sum up and tie together all of the different gas laws that we learned about previously. So as a reminder, right, we saw three different gas laws. The first being Boyle's law, which says that volume is inversely proportional to pressure, right? So if you say have a gas and you lower its volume, you compress it, right? What that's going to result then in is a higher pressure. So as volume decreases, pressure increases, and vice versa, right? So they are inversely related. The second law that we looked at was Charles's law, which says that volume is directly proportional to temperature, right? So I think a good example is like if you have a balloon out on a hot day, then if it gets hot enough, then the gas expands so much that it actually exceeds what the balloon can handle, and so then the balloon pops, right? The volume just becomes too much. And then lastly, we saw Avogadro's law, which says that volume is directly proportional to amount or moles of a gas. So this one is pretty intuitive. I think of like if you have a pump to fill up your bicycle tires, right? As that pump is going, you're just pressing more air into the container, and so that's going to inflate the tires, right? Increase the volume of the gas in those tires. And so from all of these different laws, right, we can kind of see how each of the different properties, pressure, temperature, and moles, are related to volume. So we could kind of summarize all of these or put them all together into really one relationship, which I have right here as volume is proportional to NT over P, right? So this incorporates like all of those different laws that we saw previously. It just kind of meshes them into one thing. Now, kind of just rearranging this, we have pressure times volume is proportional to moles times temperature, or PV alpha NT, right? Remember that these little alpha symbols just mean proportional to, and so from these relationships, we can kind of see then, okay, if I increase pressure, what is that going to do to temperature? Or if I increase volume, what does that do to pressure, right? All of those things are kind of accounted for here. The only thing is that it's not like, I guess, directly like a one-to-one relationship always. There is some kind of constant that relates these. And so we'll express kind of this relationship here as PV equals nRT. And so we'll discuss R in just a moment here, but right, this rearrangement, this formula is referred to as the ideal gas law. It's really the all-encompassing law that holds within it, right? Boyle's law, Charles's law, and Avogadro's law, all of those are kind of meshed into here. Those previous laws are still held true. We still have these relationships between volume and temperature and volume and pressure and all of that. It's just kind of more neatly packaged in our ideal gas law equation. Now let's get into that new variable in there, because you've seen P, V, N, and T before, but this R bit, right, is just one additional factor. R is called the universal gas constant or the ideal gas constant, and it's really just like kind of a scaling factor so that we can make this equation actually true, right? PV is not directly equal to N times T, but if we kind of throw this R multiplier in there, that makes this equation true. Now R as a value is written out right here. I'll usually end up shortening it to just 0.08206 liter atmosphere per mole Kelvin, but the value that's on your formula sheet and the value that we should really use in class to avoid any kind of rounding errors or loss of significant figures is listed right here. Now, one caveat that I will mention is that if you look up like the ideal gas constant or R constant or whatever, you'll actually see some different values for it because there are different applications to this constant. For our purposes, we're going to be using it in this format and with these units, but right, if you find some other values online, it's the same constant, it just has different units, and so therefore kind of has these different unit conversions worked into it. But right, so looking at our R constant here and the units of R, in order for our ideal gas law to actually like work and be true, right, basically all of our different properties of the gas need to have the same units as our R constant defines them. So what I mean by that is that like pressure should be in units of atmospheres and volume should be in units of liters and moles. I mean, that one should just be moles, so that one's not hard. But then the temperature needs to be in units of Kelvin, right? That's the only way we're going to get all of our units to like properly cancel out with this ideal gas law and with this ideal gas constant. And so a lot of the problems that we'll be working with is really just a units game. It's making sure that our units match what's going on with our R constant, right? So that they can cancel out properly. But so let's look at a couple examples just using our ideal gas law and kind of connecting our different properties of gases. So first here I have this example. Say I have 2.21 moles of neon gas held in a 10.0 liter container at 23 degrees Celsius. So from this information, I have the moles of the gas, I have the volume of the gas, and I have the temperature of the gas. The last thing that I want to find out is the pressure of the gas, and I want that pressure in atmospheres. So go ahead and take a moment to work on this, right? So using the ideal gas law equation and the ideal gas constant that we have, right, you can solve for this. Just as a little note, your formula sheet actually has both the ideal gas law, so PV equals nRT, and the ideal gas constant of R. So if you have your formula sheet, you have everything you need for this. All right, so let's take a look at how we can solve this one, right? Again, we're going to use our ideal gas law of PV equals nRT. And here I've rearranged the equation to just solve for pressure. So one thing that I love about the ideal gas law is like solving for like one particular variable in it is actually very easy. If I want to isolate pressure here, then all I need to do is just divide both sides by volume, right? So pressure itself is equal to nRT over V. And so what I'm going to do to solve for this, right, is basically just use the information that I have. I know the moles of the gas that I have is 2.21. I know R, it's a constant, right, that's not going to change. The temperature that I'm given here as 23 degrees Celsius, I am going to need to convert that into Kelvin, right, in order to match my ideal gas constant. But then I'm going to divide all of that by my 10 liters, right, my volume. And so kind of setting things up here, I've plugged in my different values for N, for T, and for V, and then again I have that R as just a constant 0.08206. But so here the only change I've made is just converting my temperature that was in Celsius into now the temperature in Kelvin, right? So rather than using 23 degrees C, I'm going to set T or temperature as 296.15 Kelvin. And so when I punch this all into my calculator and I solve, I get 5.37 atmospheres as the pressure of the gas. All right, so that's a pretty simple problem using the ideal gas law. Again, what we want to make sure of is that our units of pressure and volume and temperature, right, that those match with the units of R. That way we can see kind of how all of the units are properly canceling here. We've got our liters in R canceling with the liters in the volume. We have the moles in N canceling with the moles in R, and then we have the Kelvin in the temperature canceling with the Kelvin in R as well, leaving us only with then units of atmospheres. Let's say we have a second container, also same size though, 10 liters, and it holds 2.21 moles of helium gas at that same temperature of 23 degrees Celsius. So right, in this second container filled with helium, do you think that the pressure of the helium will be less than, equal to, or greater than the pressure of the neon? All right, so hopefully you got equal to in this case. Nothing is really all that different between these two containers and these two gases. We have the same moles of each gas, even though neon has like a larger molar mass than helium. It itself is a larger atom. It doesn't really affect things. So right, kind of the nice thing about the ideal gas law is that we're assuming like ideal behavior. And so really the identity of the gas itself is not all that important. What is important is, how many moles of that gas there are and all of that stuff. But right, so here, because we had the same number of moles, the same temperature, and the same volume of our gas, we're going to have the same pressure then also. Now again, this was a pretty simplistic example, like most of the properties already had the right units that we wanted. So let's look at a slightly more complicated question. So right, say here I have 32.7 grams of nitrogen gas, and that's kept in a 5,321.8 milliliter container. So in this case, right, I want to know what the pressure is of this gas, this time in kilopascals or kPa at 718 degrees Celsius. So again, we're going to use our ideal gas law equation. We'll also definitely need our formula sheet and our different equalities and conversions, as well as the periodic table. But so go ahead and take a minute to work through this one. Try to solve for the pressure in kilopascals of this nitrogen sample. All right, so as I've said before, right, what we're aiming for with a lot of these ideal gas law problems is having the right units to properly cancel with our R value. I have R listed out right here, again, with units of liter atmosphere per mole Kelvin. And so, right, what I'm going to need to do is have my moles in moles, my temperature in units of Kelvin, and my volume in liters. In order for everything to properly cancel out, I'm going to need the following units of my other properties. And first, looking at the information that's given to us, I don't see any of these units, right? I don't see moles or liters or Kelvin, but we do know, right, different ways to kind of connect what we are given to these units. So for instance, right, although we don't have the moles of gas, we are told the mass of the gas, right, 32.7 grams of nitrogen. And so using molar mass, right, we can turn those grams into moles. Remember that nitrogen is a diatomic, so we're going to take our 32.7 grams of N2, divide that by the molar mass of N2, or 28.02 grams per mole, and then we'll end up with our moles of nitrogen out. Kind of moving through our list here, right, we want our temperature in units of Kelvin. We're given a temperature in Celsius, so 718 degrees C. If we just add 273.15 to that, right, that gives us our same temperature but in Kelvin. So right, my temperature here should be instead 991.15 Kelvin. Right, that's what we're going to use in our equation. Now, lastly, for the volume, again, I want volume in liters. I don't have that exactly, but I do have, right, the volume as 5,321.8 milliliters. I know that 1 liter is equal to 1,000 milliliters, and so I can set up a conversion factor like this one, turning those milliliters into 5.3218 liters. And so now I have all of the different pieces, right, to plug into my PV equals nRT equation. Again, kind of rearranging that to solve for pressure alone. I have nRT divided by V. That's what I've put together in my equation on the screen here. And here solving for that, I got 17.835 atmospheres. But I'm not done here, right? What this question is asking for is not just the pressure of the gas in atmospheres, but the pressure of the gas in kilopascals. So I'll need to refer to my equalities and conversions. I see that 1 atmosphere is equal to 101.325 kilopascals. And so, right, completing this conversion, I'm going to get 1,807.2 kilopascals. Now, I took care here to bold my significant figures. So really, this should be 3 sig figs. And so rounding that out, I should have 1,810 kilopascals as the pressure of this gas. But so, right, that's just kind of how we can use the ideal gas law most simply. We're going to see a bunch of different applications of the ideal gas law, kind of connecting back to some of the earlier concepts in this quarter, things like limiting reactant problems, or even like solving for density and any of that business, right? We're going to kind of see how we can apply this ideal gas law to other scenarios. But right, in terms of just using the equation itself, again, I'm going to remind you to really focus on the units for all of our different properties of the gas. But so please let me know if you have any questions, and I'm always happy to help.